In this chapter, we will introduce 4 different theories that we are going to use in welding simulation. Lagrangian, adaptive Lagrangian Eulerian or ALE Eulerian elements, and SPH method. You can see a graphical view of each theory here. This one is a model with Lagrangian theory. This one is explosive welding, and the ALE theory was used here. We have a simulation with the SPH method here, and in this one, the Eulerian elements were used. Now let's see what the Lagrangian theory is. First, you need to know that this theory is used for solid mechanics. In this method, nodes move exactly with material points. It is easy to track free surfaces and apply boundary conditions. And the mesh will become distorted with high strain gradients. For example, see this figure. If a force like an impact applies to it, the elements near the force will become distorted because we have high strain gradients. Now let's explain the Eulerian theory. This one is used for fluid mechanics. In this method, nodes stay fixed while material flows through the mesh. It is more difficult to track free surfaces. And we have no mesh distortion because the mesh is fixed. The next theory is ALE. This one is a combination of the 2 previous theories. In this method, the mesh motion is constrained to the material motion only where necessary, at free boundaries. Otherwise, material motion and mesh motion are independent. To better understand, see this figure and compare it with the previous theories. When applying the force, the software will check the element domain you have determined and decide whether or not it is necessary to remesh the domain and divide the deformation between elements equally. The last theory we are going to explain is smoothed particle hydrodynamics, or SPH. It is mainly used in fluid mechanics. In this method, there are no elements, only a collection of nodes. This is one of the meshless or mesh-free methods in the Abaqus. For more information, you could check the Abaqus documentation in the related section. Here you can learn about its boundary conditions, loads, constraints, and so on. If you don't have the Abaqus documentation on your computer, visit this website. In the last chapter, we will explain how to apply the theories explained in the previous chapter, and how many ways it is possible to simulate welding in the Abaqus. We are going to simulate welding in several ways. The first one is the common way through the Abaqus settings. In some cases, where we cannot use Abaqus settings to apply for heat flux, we could use the dflux, vdflux, or umdflux subroutine to apply for the heat flux in the simulation. The next way is the death and birth of an element. The other 2 ways are the explosive method and surface volumetric thermal flux. If you want to specify the heat flux as a function of a combination of time and position or other variables, you must use the subroutines. Here you can see the dflux subroutine interface as an example. In the user coding block, we need to define our code and determine the flux 1 and flux 2 variables. Now let's see what the method of death and birth of an element is. We use this method when we need to add or remove elements in our analysis. To better understand, look at this welding process as an example. At first, there are no elements between the two pieces. The elements will gradually be added to the model when the torch moves to join the pieces. We will explain how it's done in detail in the workshops. The explosive method is used for joining dissimilar material combinations such as aluminum and copper. For example, in this figure here, the red part is the TNT material, and when it explodes, it will join the two pieces. The final method is surface and volumetric thermal flux. We use this method in arc welding. We can create a surface heat flux load like this figure here, or a body heat flux load to simulate the welding process with the methods mentioned in this chapter.
In the next videos of this playlist, we will explore the workshops to gain a detailed understanding of how to implement such simulations in Abaqus CAE.